Okay, reading quiz 9 has to do with a technique that's called integration by partial fractions. Basically, the idea is that we're going to use fractions and what's called partial fraction decomposition to help us figure out our antiderivatives. Oftentimes we'll encounter the natural log function, which we'll see in just a minute. So, in order to integrate certain rational functions, partial fraction decomposition is necessary. In essence, we're going to decompose the denominator of a rational function into smaller parts. So we need to get some practice with that first. As we'll see, the antiderivative of a rational function can involve other rational functions, arctangents, and logarithms. So a wide variety of possibilities here. So let's talk about partial fraction decomposition. Dealing with proper fractions when the denominator degree is larger than the numerator degree. For example, we've got 1 over x minus 2 times x minus 5. How do we decompose this? Well, step 1, rewrite the rational as the sum of linear factors using factors of the denominator. In our case, we've got x minus 2 and x minus 5. And we're going to say a and b are the constants that we don't know yet that will decompose our fraction. So 1 over x minus 2 times x minus 5 is going to be equal to a over x minus 2 plus b over x minus 5. Our first step is to clear the denominator. And what that means is we need to make sure that we find common denominators. In our case, the x minus 2 times x minus 5 is a common denominator for both fractions. So we rewrite a times x minus 5 over x minus 2 times x minus 5 plus b times x minus 2 over x minus 2 times x minus 5. And you'll notice that the denominators match, and therefore we only need to compare our numerators. So we can set up an equation that involves those numerators. A times x minus 5 plus b times x minus 2 would have to be equal to 1. So I rewrote it here so that we could see this. Solve for a and b. So here we have a couple of options, but we're going to use what's called the Heaviside method, which will help us figure out what a and b are. And the trick is to make the factors equal to 0. In other words, the x minus 5 factor equal to 0 and the x minus 2 factor equal to 0. In the first case, we're going to set x equal to 5. And when we plug in x is equal to 5 into our original equation, we notice that we get 0a plus 3b is equal to 1. And immediately this gives us that b is equal to 1/3. Next, we're going to try setting x is equal to 2, making the second part equal to 0. And when we do so, we get negative 3a is equal to 1, or in other words, a is equal to negative 1/3. When we plug this back in, we see that this means that negative 1/3 over x minus 2 plus 1/3 over x minus 5 matches our 1 over x minus 2 times x minus 5. And you can see the work that I did down here to combine the fractions back together and show that this is the same thing. Pretty cool technique. So let's try this again with 3 factors. Let's say we had an x plus 3, x plus 5, and a 3x minus 2 on the bottom. Well, we decompose that into a over x plus 3 plus b over x plus 5 plus c over 3x minus 2. We rematch our denominators, so the a gets an x plus 5 and a 3x minus 2. The b gets an x plus 3 and a 3x minus 2, what it didn't have originally. And the c gets an x plus 3 and an x plus 5 in its numerator. It looks bad, but it isn't really too bad since we already matched the denominators. Now we just have to worry about making sure our numerator matches. So all of this, a times x plus 5 times 3x minus 2 plus b times x plus 3 times 3x minus 2 plus c times x plus 3 times x plus 5 has to match this numerator of x squared plus 3x minus 44. Well, now that we have our technique of setting each factor equal to 0, we actually can get this to go pretty quickly. If, for example, we set x is equal to negative 5 at first, the only thing that's not affected is the part with the b. And when we plug in negative 5, we end up getting 34b is equal to negative 34, and b is negative 1. Then we're going to let x is equal to 2/3. That's when 3x minus 2 is equal to 0. When we work all that out, we get c is equal to negative 2. And when x is equal to negative 3, we get everything but the a term. So when we work that out, we get negative 22a is equal to negative 44. So a is equal to 2. And step 5, we plug a, b, and c back in and find that this wonderful fraction decomposes to 2 over x plus 3 minus 1 over x plus 5 minus 2 over 3x minus 2. It's pretty amazing how you can get that to simplify so well. So let's look at some variations on the theme. First, how do we decompose if a factor repeats? Well, we have a rule for the situation, and the rule is we write the factor twice if it's a squared. So we're going to write 4x over x minus 1 squared times x plus 1 as a over x minus 1 plus b over x minus 1 squared plus c over x plus 1. Notice the x minus 1 is written as a repeated factor. That's because we want to capture the x minus 1 twice. So from there we get a times x minus 1 times x plus 1 plus b times x plus 1 plus c times x minus 1 squared, that is rewriting all of the factors we're missing, is equal to 4x. So we get two options. We can set x is equal to 1. When we do so, we end up with 2b is equal to 4 and b is equal to 2. We can also set x is equal to negative 1, which cancels out everything but the c factor. And we get 4c is equal to negative 4, and then c is equal to negative 1. Then we can use any other value of x to find out what a is. For example, if we set x is equal to 0, then we end up with negative a plus b plus c is equal to 0. Well, we know what b and c are. We can plug those back in, and then we can solve for a to get a equal to 1. We get our final answer of 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1. Okay, we won't see much of that in this course, but I thought you might want to have a look at it just in case it comes up in future courses. This next item we'll see frequently. If the numerator and denominator have the same degree, or if the numerator is a higher degree than the denominator. You'll notice in the previous examples, like example 2, that the denominator was a degree more than the numerator. So, for example, if we want to decompose x squared plus 3x minus 4 over x squared plus 4x minus 5, the first step is to rewrite the fraction as the following fractions. The denominator we're going to write as numerator over denominator. In other words, x squared plus 4x minus 5 over x squared plus 4x minus 5, which, as you'll notice, reduces to 1. And then we're going to write a second part as plus a over x squared plus 4x minus 5. And in the first fractional part, we're making the numerator the same as the denominator. Sorry about that. So, in order to find the value of a, we're going to find the original numerator minus denominator, which will be x squared plus 3x minus x squared plus 4x minus 5, which is negative x plus 1. And I hope you notice that the way that I've rewritten this, we've got x squared plus 4x minus 5 plus a minus x plus 1. And if you add the two numerators there, you're going to end up with an x squared plus 3x minus 4, okay, which is exactly what we want. Notice also that this first fraction reduces down to 1, and that's pretty cool. What we've essentially done is we've done long division in a little bit of a different way. So what's the point of all this? If we can simplify a rational function by factoring its denominator, we're going to have a better chance of being able to integrate that function. So looking at example 1 again, if we wanted to integrate dx over x minus 2 times x minus 5, we've already found out through partial fraction decomposition that can reduce down to negative 1/3 over x minus 2 plus 1/3 over x minus 5. So this means that we can rewrite our integral with those two fractions, the integral of negative 1/3 over x minus 2 dx plus the integral of 1/3 over x minus 5 dx. When you integrate each part separately, both of those integrals will involve a natural log. Negative 1/3 natural log of x minus 2 plus positive 1/3 natural log of x minus 5 plus c, which, yes, I will ask you to simplify. In this case, we can simplify to 1/3 natural log of x minus 5 over x minus 2 under the absolute value plus c. We can also move the 1/3 in, but you've got to be able to understand how this simplifies. And the reason why the x minus 2 is on the bottom is because there was a negative exponent out front. Again, we found out earlier when we wanted to decompose x squared plus 3x minus 44 over x plus 3 plus x plus 5, or times x plus 5 times 3x minus 2, that decomposed to 2 over x plus 3 minus 1 over x plus 5 minus 2 over 3x minus 2. So this means that we can then break up our integral based on those fractions. We've got an integral of 2 over x plus 3 dx minus the integral of dx over x plus 5 minus 2 times dx over 3x minus 2. And we can then integrate each part separately. All three of them involving natural logs. 2 natural log of absolute value of x plus 3 minus natural log of x plus 5 minus 2/3 natural log of 3x minus 2. Where does the 2/3 come from? Well, the 2 comes from the integral itself, and the thirds comes from the fact that the integral has a 3x on the inside. And by substitution and chain rule, we need to account for that by dividing by an extra 3. Because when we take the derivative of this, we're going to get a 3 to come out that we don't want. So I say down here, watch out with the 3x minus 2 portion. Don't forget about u substitutions. And the simplified version is right there. Example 3 revisited. We want to integrate the 4x dx over x minus 1 squared times x plus 1. We already found out how to decompose that. And so when we integrate, we're going to integrate dx over x minus 1 plus 2dx over x minus 1 squared minus dx over x plus 1. The first and the last integrals will involve a natural log of absolute value of x minus 1 minus natural log of absolute value of x plus 1. This second integral, be very careful with that though. This is the same as 2 times x minus 1 to the negative 2 power, which will integrate then to negative 2 over x minus 1. So a little bit different here because of that extra x minus 1 squared factor. In example 4, we're going to integrate x squared plus 3x minus 4 over x squared plus 4x minus 5 dx. And we found out earlier how to decompose that. That was the trick of long division. We end up getting 1 plus negative x plus 1 over x squared plus 4x minus 5. If we factor the denominator there, we'll notice that the x minus 1's canceled. That doesn't always happen. It just so happened here. And so what we need to integrate when we're integrating the original is just 1 minus 1 over x plus 5. When we integrate 1 dx, we're going to get x. And when we get dx over x plus 5, we get natural log of absolute value of x plus 5 plus c. And notice that this one doesn't necessarily always involve natural log, but most of the time we get some sort of a natural log involved.